Have you ever stopped to wonder how your computer is streaming music, running a dozen browser tabs, and downloading a huge file all at the exact same time without just, completely melting down? It really does feel like magic. But today, we're going to pull back the curtain on that magic trick. So here's the big question. How can one single brain, one computer processor, seem to do hundreds of things simultaneously? Well, the secret is, it's not. What you're actually experiencing is this masterfully crafted illusion of multitasking. And at the very heart of that illusion is something called CPU scheduling. To really get our heads around this, we're going to use an analogy. So for a minute, forget all about processors and computer code. Instead, I want you to picture a single, incredibly fast master Lego builder. This builder, well, that's our CPU. And all those tasks you give your computer, think of them as Lego instruction booklets. Okay, so if you're this Lego builder and people just start handing you instruction booklets, what's the most obvious way to work? You'd probably just build them in the order they show up, right? First come, first built. This approach actually has a name, first come, first served, or FCFS for short. It's super simple, and you could say it's fair. The builder takes the first booklet, builds that entire Lego set from start to finish, and only when it's completely done do they even look at the next one. But as you're about to see, this simple method has a huge drawback. And this paints the perfect picture of the problem. Imagine someone hands our builder the instructions for a massive 5,000-piece Death Star. But right behind them is a kid who just wants a simple, tiny 10-piece race car built. With our current rule, that little race car has to wait for hours while the entire Death Star is put together, piece by painful piece. This is called the Convoy Effect. And if you look at the numbers, you can really see this in action. Take a look at process 3, P3. It only needs 3 units of time to finish. It's a super quick job. But because it had the bad luck of getting stuck behind that massive P1, it had to wait 27 units of time just to get started. That is just incredibly inefficient. Clearly, that's not going to work. We need a smarter system. If you were the builder, you'd probably think, okay, maybe I should just look at all the booklets first and build the quickest one to get it out of the way. And that's exactly what our next algorithm does. This is called shortest job first. The builder scans all the waiting instruction books, picks the one with the fewest pieces, our little race car, and builds that one first. And this dramatically improves the average wait time for everybody. But this new focus on speed, it introduces a totally different kind of fairness problem. And here is that new problem, starvation. What happens if people just keep showing up with small, easy-to-build race cars? Well, our builder, by following the shortest job first rule, will always pick those small jobs first. And that massive, important 5,000-piece Death Star, it could, in theory, just sit on the to-do pile forever, constantly getting pushed to the back of the line for smaller tasks. It's literally starving for attention. Okay, so there's another wrinkle here. Can our builder be interrupted? In what's called a non-preemptive system, once the builder starts a project, they are locked in. They finish it no matter what. But in a preemptive system, they can be interrupted. So imagine they're halfway through a 100-piece model and someone brings a new 10-piece race car. A preemptive builder can actually put down the current project, quickly build that new, smaller one, and then go back to the bigger one. So far, we've been all about finishing jobs as fast as possible. But what if the goal isn't just raw speed? What if it's about fairness and making everything feel responsive? This brings us to a whole new way of thinking, one that you experience every single day. Meet the round-robin scheduler. The philosophy here is super simple. Everyone gets a turn. The builder sets a timer, let's say for 2 minutes. They work on the first Lego set for exactly 2 minutes. When the timer dings, they stop, put that set at the back of the line, and then spend the next 2 minutes on the next set. This way, everyone gets to see at least a little bit of progress. You know that fixed slice of time, the 2 minutes in our example? Well, it has an official name. It's called the time quantum. And choosing the right size for this is absolutely crucial. If it's too long, it just starts to feel like our old first-come, first-served system. But if it's too short, the builder wastes all their time just switching between projects. And this, right here, is why your computer feels alive. When you're typing in a document while, say, a huge video is rendering in the background, this is what's happening. The CPU gives a tiny slice of time to your typing, then a slice to the video, then back to your typing, switching so incredibly fast that it creates this perfect illusion that both are happening at once. Okay, so we've seen a few of the basic strategies, But how do real operating systems, like the one on your computer right now, actually think? The truth is, they don't just pick one strategy. They use a really sophisticated combination of all of them. To build a really good system, engineers have to measure its performance. They look at stuff like CPU utilization. I mean, is our builder actually busy or are they just sitting around? They look at throughput. How many complete Lego sets are we finishing per hour? And critically, they look at response time. How long did you have to wait just to see the first sign of progress? When you're clicking on things, that last one is king. Let's talk about utilization for a sec. You might think you want the builder busy 100% of the time, but that's actually not the case. Real systems aim for a sweet spot, usually between 40 and 90% busy. This leaves enough breathing room to handle new, urgent tasks without slowing everything to a crawl. So this is where it all comes together. The real-world solution is called the multi-level feedback queue. It sounds complicated, but stick with our Lego analogy. Just imagine our builder now has several workbenches, and each one has a different priority. The top bench is for super quick, interactive jobs, like you clicking a button. And the bottom bench? That's for the giant, non-urgent projects, like our Death Star. Now here's the feedback part, and honestly, it's genius. If a task on the high-priority bench starts taking too much time, if it's being a CPU hog, the system automatically moves it down to a lower-priority workbench. This makes sure that long-running processes can't ruin that responsive feeling for all the quick interactive tasks. It is a self-correcting system. So as you've probably figured out by now, there's no single best solution. There's no magic bullet. Every choice we make is a trade-off. Every single algorithm prioritizes one goal, and usually it's at the expense of another. It's the ultimate balancing act. And just when you think you have it figured out, modern computers throw another wrench in the works. We don't just have one Lego builder anymore. We have a team of 2, 4, 8, or even more, all working at the same time. So now the challenge isn't just deciding what to build next, but which builder should build it. And that really brings us to the core takeaway of all of this. CPU scheduling is a constant negotiation. It is a balancing act between these competing goals. You have fairness versus efficiency, and you have throughput versus response time. You just can't always have both. And that elegant, invisible system, that's the secret behind how your computer juggles everything you throw at it. Thanks for watching. See you tomorrow.